Not for certain. Okay.
It is a lot.
I got there yesterday. I wonder if
Alright, so, as Alex reiterated on Tuesday, this particular subset of materials you are not responsible for on the upcoming midterm. At the same time, certain parts of what we're going to discuss today may be especially useful for, say, the final part of homework 5 and or for your future kind of individual projects and things as we go. So today's lecture, we are going to be covering the basics of D3 layouts. So when we usually hear layouts, what we think about are kind of some sort of system of spatial organization for things, right? The way in which parts of something are kind of arranged in a kind of a screen. In D3, layouts do kind of handle arrangement, but they only do so in the context of data transformations. D3 layouts don't actually provide any visual output or do any drawing for you. What they're doing is simply taking one data set and transforming it into another data set that you can easily bind to your data to do the visualization yourself, right? So, why would we want to do this? Because I don't want to manually try to figure out how to turn this matrix into all of the requisite parts of that figure over there, which is called a chord plot or a chord diagram, right? So instead, we let D3 layouts transform the data into something that looks like this, where all of a sudden each one of these arrays here represents one of those kind of chords going across the center, and these end groups and angles are kind of the edges of your plot around your circle, right? So it's automatically doing all of some pretty hefty data translation for you. So that's what D3 layouts do and why you probably want to use them. But the D3 data bind and draw call is all you. So, D3 has a whole bunch of different layouts. This one's for a chord diagram. We've also got things for like a tree map, for circle packing, for force-directed layouts for graphs. And so there's a whole bunch of them here. We're not going to go through every single one of them. so when you're looking for your own projects and whatnot, be aware that these exist and maybe go looking to try and kind of make sure what's out there in terms of what you want to be able to use. For today, we're going to start by walking through a couple of different examples in the hopes of giving you some basis for how these work and what they look like in practice, from something super simple to some of the more complex things that are in the interactive content that is currently linked on the homepage. So we're starting with kind of brief overview of what this is going to look like in pie charts, and then we're going to move over into the interactive content, which is where the rest of kind of everything we'll be discussing will be available for you after class. So, pie charts. So, assume we have a data set that looks like this, or specifically this data set, and we want to make something that looks like that pie chart over there. Now, I believe we've talked in class about pie charts are bad for any number of things, particularly usage, but in this case, it's simple, right? This is going to be, anything else is going to be more complicated. So let's deal with the simple version of this data transformation first. So, the D3 pie call, this is kind of that kind of transition creation call, like we saw the list of them before. So D3 pie is going to take in this data set and it's going to create another data set. Specifically, it's going to create a data set that contains all of the angles that you need for each of those different things to create your pie chart. So specifically, if you were to log pie.data after having called this, you wind up with kind of, you've got the actual data itself, you've got the value that we decided to pull from it and bind to it, and you've got a index, which is just kind of the index in the data array originally, and a start angle, a pad angle, and an end angle. So these angles assume you're in radians, so these go from 0 to 2 pi. So what we're looking at for this first element is the specific start angle is at 0, so this is, and it goes to 5, which is kind of 2 pi is right around 6 point something. So like this is your green section right here that you've got your start and end angle for. Pad angle is simply going to, and we'll do this in interactive content, but basically add some spacing between each of kind of the various curves within your pie chart, or arcs, if you will. And I say arcs because that is the second command. So pi is doing the data translation. D3 arc is a generator like our D3 line generator or D3 area generator that's going to take in data and create specifically arcs. And so the padding, for example, will be accounted for by the D3 arc generator. Okay, so now let's actually look at what this looks like in kind of the full version over here. That's lecture. So here's the beginning of the layout section and the interactive content. This intro to Doughnut Charts is everything we just talked about. And here is the full kind of code that we're going to go through. So we've got our data set here, width, height, definition of the radius of our pie chart so that it's visible within our SVG, the creation of our SVG. This is a color scale. I can't remember if we actually dealt with color scales specifically with you guys. I think we've talked about them, whether or not you've had to deal with them in the homework or not. But basically what this is doing is this is like any other D3 scale, taking a value and returning a value. In this case, it is taking an index value and returning a specific color value that you're going to use for fill. The D3 pie call here is the creation of our layout generator. Note that we are not passing the data to it yet. We are then specifying how we want the generator to handle values. So if we go back up to our data, our data are objects that have OS and share. Yeah, question?
If you zoom in a little bit, it's kind of
Better? Perfect. All right. So our data has OS and share. How is PyGenerator supposed to know what the heck it's using to actually generate and create kind of your various data arcs based on data? Well, you have to have some way of telling that generator how it's going to pull a given value out. In this case, what we're going to do is we're going to take a given data object and we're going to take the share attribute from it, which is a value, and that's what we want to use for our pie chart. You can also do a whole bunch of other customizations on the generator. So pad angle, let's add that one in for now. And start angle, end angle, basically, if you wanted to make your pie chart just like a semicircle, not that that's going to be readable for anybody, but if you wanted to do it, you could set default start and end angles to something other than a pie chart and create a diagram. This is the code to do that. Yeah.
Can you use that to change the direction that it's appearing?
Not positive off the top of my head. The D3 API will definitely tell you though. And we can test it, but let's test it after we get to the end. So remind me when we get to the end of this section. So once we've set up our transition, or sorry, not transition, our layout generator, what we are going to do is we are going to call and kind of pass it our data set. And we can console log the result of that. Pull this up over here, which is really, really tiny. So let's expand that for you a little bit. And this is the pie data right there. And we're seeing exactly what we were looking at before, where the value is now the share that we just pulled out of it. And we've got kind of angles for each aspect of our pie chart. And next, we are going to call or create the D3 arc generator. Similarly, we can set various attributes to the D3 arc generator, the most important being outer radius and inner radius. You can also do like a pad angle on the arc generator. From not recommended by comparison. When people read pie charts, they read them based on area judgments, something other than central angle usually. And because of that, padding the angle is going to create kind of off-center judgments, or rather biased judgments. So in the case of pie charts, you probably want to pad the original pie rather than the arcs. But you can pad the arcs. You can also create corner. We'll come back up. We'll show you what some of this stuff looks like. But basically, arc of, you call it on the pie data, and it's going to generate a series of paths, just like we've had paths for everything else that we've discussed. And so then your draw call is going to be kind of the exact same thing. We're going to create a group that binds our pie data to it. We are going to append paths and create kind of path arcs for each of those paths created by the arc generator. We are going to fill them with color based on the OS that we're passing in. And then we add a text label down here. And so the end result is something that looks like this, which is pretty much what we had before, but with the padded angles. So if we put the padded angle in like 2, we get smaller paths on our angles. Okay, so the question was, can we reverse the polarity here? So let's try, I'm thinking it doesn't, but if you went from...
Let's see what this does first.
Oh, this? So this is negative pi over 2 to pi over 2.
What does that look like?
So if we think about kind of that coordinate space that I laid out before, right? 0 is at the top, pi is at the bottom. pi over 2 is on the way out over here, and then you've got 3 pi over 2 over here. So negative pi over 2 is the same as 3 pi over 2, right, around this circle. So from negative pi over 2 to pi over 2 means we should have a semicircle down bottom, which is exactly what we're seeing. All right? And if we decided to do negative 2 pi to 0, I think it's just going to be a full flip all the way around. What did I do?
Oh, yeah.
Yep. And yeah, negative 2 pi to 0 just goes all the way around. So I am sure that there is a way to flip the polarity in the direction. I just do not know what the command for that is off the top of my head. The other things here that we can show you exactly how they're going to work. Who can tell me what the heck's going to happen if we change inner radius versus outer radius here? So, yeah.
So like if you change inner radius, it's going to make it like a donut.
Exactly. So because you're dealing with angles only, right, the difference between a pie chart and a donut chart is simply that one of them has a kind of hole cut out of the center of it. So inner radius and outer radius, if we want to turn this into a donut chart, we simply do radius minus 30 or something like this, and we've got a donut chart. Right? Because all we're doing is creating a path and creating a, right, so the arc generator is creating a path. That path is being based on some radius, which is specified to the generator, and the angles that we're passing in. And so if we specify inner radius, outer radius, that changes how the arc generator shows the path. Does this make sense to everybody? Okay. We can, just to show what some of this stuff looks like, say we want to do the arc pad angle instead. That's going to look like this. Not a hugely visible difference in this case. We can add a corner radius of, say, 5, and all of a sudden we have nice kind of corner radiuses. If we up that back to what we were looking at 30, then we've got nice rounded corners here for each of our things. And then the only other thing in this code that we haven't fully discussed is the use of arc centroid. So arc centroid specifically is a call that is going to find kind of a quick, so it's not actually the geometric centroid of the path, but it is something that reasonably approximates a kind of position centered in the kind of area that is being drawn, is the easiest way of thinking about it. If you want to go digging more into what exactly is happening with arc centroid, feel free. But for our case, arc centroid is allowing us to create a text label and to shift it around such that it's still on top of the relevant portions when you're out here versus when we do, let's make it 30 here, there. Right, so what it's doing is it is basically giving you a label position that is guaranteed to be on your elements. Cool. So now we've kind of walked through a simple example of what exactly a D3 layout is, what it does, how we use it in a full code example. So now we're going to go on to that crazy chord diagram that we were looking at before. All right, so here is that same data set that we were looking at. And here, as one might expect, the first relevant function that we care about is D3 chord. And so this is analogous to D3 pi. And this is going to create the various data elements we need. As we saw briefly, for those who have a photographic memory, when I threw up the version of what the chord diagram looks like, you know what, we should be able to do it over here. Yeah. So this is what the output of D3 chord is going to look like. Each of these is going to be kind of the chords going across, and you're also going to have the various, or ribbons rather, going across, and you're going to have the various angles for your original outer edge, right? So as you might expect, D3 arc we're going to use again, because that's how we're going to define the outside edge of our circle. And D3 ribbon is going to handle the draw of the actual ribbons and chords across the center of your diagram. So the return value of D3 chord has source and target, where source and target here for each of these ribbons are indexes into this particular set of groups that define our arcs. So this shows us that we have kind of a set of hierarchical relationships. If we go back to kind of why you would want to use D3 chord and what this matrix is telling us, basically you can think about this as we have 4 different quantities here, and we want to show the links among those 4 different quantities, both to themselves and to kind of one another. And that's what's being represented here. So directed relationships among groups of entities. So source and target are the specific groups that you want to show the relationship between, and each of these chords is encoding a given relationship. And then, like we had before, you've got the start angle and the angle sub-index for each of your groups. The sub-index is simply what's, again, being used for those relationships. And kind of we talked about kind of the actual groups. It's the exact same for pie charts. So what does this look like when we go to draw it? We start with our matrix here. We create our SVG, define an inner radius, outer radius of whatever we want. So in this case, we're defining an outer radius that is kind of 30 pixels wide to create a large bar at the back there. So if we look at this thing, right, fairly large bar here. If we wanted to thin that down, we could do 15. Right? Cool. So inner radius and outer radius. We've got a color scale again. We've got the actual chord call here, where we're adding some pad angle padding to kind of the chord diagram to create those nice kind of white gaps and clear separation between each of our different groups that we're trying to show the relationships between. Our arc call, just like before, is inner radius, outer radius. And so our new calls here are D3 ribbon, which we are going to use. It only has one radius, and here we're using inner radius. If we were to change that, what's going to happen? Bueller? So if we think about what's going on with ribbon, ribbon is taking each of these source backs, and it's drawing. So you can think about this guy right here is like one of these elements right here. So if we change the radius that's being used to draw that, then it's going to change the radius that's being used to draw all of these elements. So let's do that. Inner radius minus 10. Right? So this is an independent draw. You can set the radius to whatever the heck you want. If you help them match up, it's going to be readable, but like you can technically do lots of things that maybe you shouldn't. And so, right, the radius call here, we only have one radius rather than an inner radius and an outer radius because there's only one radius that's going to be used by the ribbon generator. And we can log the chord matrix, which we did. And okay, so the actual draw call, now that we've set all of that up, we've got our arcs, we've got our ribbon generator, both of them tied from our chord layout, and what we are going to do is we're going to create our groups. We are going to set the data to kind of our chord layout output. So note here, we are using a .datum call. This is something that I am going to mostly gloss over. You can imagine that .datum, like .data, is setting a data object for a single thing. Now, when you have multiple things in your selection and arrays of things, all of a sudden that does random weird things that you might not anticipate, but might want to use for given reasons. And there's lots of stuff in the API about all of that if you get there. However, for our purposes today, .datum is just a way of associating a single data object with a single SVG object. Cool. So, we've created a group object, appended it to our DOM, and we've associated data with it. That is all this call is doing. So, we can then append another group element to that using the groups from our chord data, which is this over here, right? So can anybody tell me what we are likely going to do with this without kind of glancing just further down the page? We're going to use this group to create that outer edge of our chord diagram, right? So we've associated kind of the data for this group as the specific subset of array of groups there. And then we're going to append paths, where each path is the arc generated by a single member of that group. Recall that if you pass a function to an attribute, this is the exact same as if we've done that, right? So we've got the arc for our given kind of data. We've got a color that we're setting. We've got a stroke that we're setting. And that's creating this outer edge. And if we comment out the rest of this, which we could do just for visual, what we should have left is just that outer circle, like our pie chart before. Great. Okay, so now we're going to add our ribbons back in. And here, so ribbons is we're going to append another group. We are going to create select paths from it. So here we're going to use the proper D3 selection basis that we had before. We weren't above. And that's dangerous, so don't do that, kids. Here you're basically going to do kind of your select all paths. We have all of our data elements are all of these various chords. We're going to do an enter append. We're going to set the actual path for that path to the output of the ribbon generator. We'll set a fill, we'll set a stroke, and the end result, we can actually comment that out as a function, it's not doing anything right now, is that we've got kind of the basis of the chord diagram here. The only other thing in the rest of this code, which is almost about a third of everything here, is how are we doing all of those fancy ticks? Because that can get interesting. So basically, what's happening here, and feel free to look at this stuff for future reference if you want to. But we're defining a custom function here called group ticks. And this is going to return an array of the various angles and values needed for the ticks for a given group and step size. So here is going to be one of our groups here, which has angles. And step is going to be whatever step size we decide we want for our ticks. So in the case of what we wound up doing here, we did it by thousands. 1E3 is just scientific notation for 1,000, right? So this is creating, what this function is doing is kind of we're going through, we're getting the full length of our angle, dividing it by the overall value, and we're doing a D3 range, a D3 mapping of that data set to get equally spaced values across it. Format value, did we cover formatters? I don't think we did, but I wanted to double check. Basically, you can read the API on this. This gives you a lot of control over pre-formatting text labels. So you can use decrease for some of this stuff. For example, we didn't have this, or we changed this to something else. Now we've got 25,000 written out like this, whereas because we're using the formatter and we set it to thousands and we've got our, go read the API if you're interested. I don't need 5, that's going to be wrong. 3, right? We've got 10K. That's a little bit easier to read, and you don't have to worry about kind of things jumping off into your map when you're dealing with really large numbers, right? So that's all that formatter is doing. So we've defined them here because we're going to use them below. To actually create the ticks, we're creating a new group, selecting it called group tick. We are binding data to it using kind of that exact group ticks function we just did with thousands. This is the enter pen for the group. We're giving it a class, we're giving it a transform, and then we're taking that group and we're going to start appending lines to each of those groups. And then, so group tick append lines, because we have all of those individual ticks. If we take out this, I can't just use comment there, I've got to do this one. That's giving us all of the nice little ticks, right? And then what this last piece is doing is we are filtering the values modulo 1,000. So only if they're on the thousands, and we're taking those ones. We are appending the 5E3, so every 5,000, I'm sorry. We are appending text on those particular elements and doing transforms, text anchor, and formatting the value using our value formatter, and that's giving you the 0, 5K, 0, 5K, 10K, etc. coming around the outside edge of this. Fairly straightforward. Okay, so we've gone through pie charts, we've gone through chord diagrams. The next thing, and this is where you probably want to wake up if you're working on homework 5, is tree layout. So we have you manually do all of the kind of back, forth, parent stuff back in homework 2 for trees. D3 will handle that for you in a beautiful way. So when you looked at homework 5 and saw that final part 5 piece that was like, oh, create this tree over here, and you're sitting there in a cold sweat, no worries, we got you covered. Hopefully that should be a little bit simpler after this lecture. And so trees are kind of commonly used for hierarchical layouts, as one might expect. And basically, D3's hierarchical layouts expect hierarchical data being pulled in. There are 2 ways you can handle this. Either your data is hierarchical to begin with, which JSON can be. So in this case here, we've got a JSON object that is hierarchical, that are like children of Adam and Eve, but Adam's missing, so just children of Eve, right? And I'm not the one that came up with this. It's in the documentation. That's the data set they use in the documentation. We're just being consistent. Not my problem. Okay, so hierarchical data.
Documentation being the Bible, or
No, the D3 documentation. Create the D3 hierarchy is literally just calling D3 hierarchy on that data. There's an optional argument children that you can pass in, but in this case, which that optional argument for children will be a way to actually specify which part of your data object are the children that you are trying to be associated with. In this case, we have a attribute named children, so it's just going to use that. It's going to be great. But if you didn't have that, that is where that second argument comes in. And that's going to return a root node of Eve with all kind of your, just like we did in homework 2, everything having been created for you. Yes, question? Why is what? So this is not, so the brackets here are listed in documentation, and it's a lot easier to see when it has little fonts on it. There is no additional argument here. This is not an array accessor of data. This is, it's required to have data, and it takes a second argument that's optional, that's children. So if we, this might be easier to clarify, just going to D3 hierarchy. So this is exactly what it's looking like. It's in a different font here because fancy rendering. But basically, this is saying that it can have one argument or two arguments. It always has to have the data argument. It may or may not have a function that is defining what children are. Okay. This is the exact same data to that JSON object, provided in the way we handed you the data for homework 2, which is similar to as if you pulled it out of the CSV file. So here, we've got our names and our equivalent parents, and we've got these objects. This is not hierarchical. D3's tree layout does not automatically take this. So what we have to do is we have to wrangle that into a hierarchy first. The relevant function for this is D3 stratified. So D3 stratified on this data is going to generate a new hierarchy for the specified tabular data. So here, we're going to create the layout generator. We're going to associate a given ID with that layout generator and a given parent ID with that layout generator so that it knows what it's supposed to use as kind of the creating the node itself and associating that node with another node being its parent. And that then is going to give us a hierarchical object that can be passed through. And both of those are going to create the exact same thing. If you adjust on hierarchy on this, or D3 stratify on this, both of these return a root node that looks like this. Right? So we've got the node itself, which has the actual data associated with it. We've got its ID. We've got a parent. We've got the depth in the tree, and we've got a height, which refers to the number of the greatest distance from any descendant leaf for internal nodes. So basically, how far down the tree goes, right? So in this case, because if we look back at our data set, we have Eve, we've got the direct children of Eve, and we've got at least one other one of her children here, then that's going to be the height of this tree is 2, right? And we know that based on our root. If we were to actually open up Seth here, he'd have a height of 1 because there's a subtree below him, etc. So that's all of kind of the base descendants here. Every single kind of your original root and every single descendant of that root has these same core properties. The only one that we haven't talked about yet is value, which is a summed value for the node and its descendants. If you want to use that, then you actually have to call something else on this on the layout itself. There's a sum function that will go through and create the actual sums for you. You can reorganize things with sort and things like this. All in the documentation. We'll get to some of it later in more complex examples. But for the purposes here, you're always guaranteed to have these first 5, and this last one is going to be there, but only if you go through and do some additional function calls. The other thing that should be known about this object are there are 2 kind of built-in functions in the prototypical object that you may find very useful. Node.ancestors is going to take the current node I'm at and return all of the specific ancestors all the way back up to the root. And nodes, was that a question?
I just said that's nice.
Yes, it is nice. And then node.descendants is going to return the array of all descendants and each child in topological order. So convenient accessors for you to use, which we will use in the example. And so once you have the root node that is created by kind of stratify or D3 hierarchy, that root node with this entire node-based structure is what gets passed into D3.tree. And so D3.tree is going to actually assign the x and the y coordinates to the given node so that we can draw them. So, what does this look like? We've got some CSS up here. We've got our D3 library. Here we've got a different tree data set that simply contains a top level, a second level A and B, and then a third level, what we're calling son of A and daughter of A for I don't know what reason. But the end result is that you're going to have something that looks like this, and we can do fancy things like that. Ooh, yeah. All right. So rather than launch you through all of the crazy code that is required to do this, and then show you that at the end, let's show you what we're working to and why some of this stuff is complex. All right. So here's our original data. We've got some margins that we're using to set for our SVG. This is a common pattern that's used. I think it was used in the homework board data as well. This is just a nice way of automatically setting margins for a given SVG and having access to it all later. Here, we're simply appending the SVG object, and we're appending a group to it, as one might expect. Here we've got a couple of convenience variables, I being an iterator, 0, a duration of 750, which is going, or I is actually an index, sorry. Duration is going to be for all of our transitions, how long we want them to take. And root is going to be kind of that exact, the creation of the D3 stratified, that exact node structure we needed before. Yes, question.
So like when you define, in this case, you're defining root, is that because like you're going to use that in multiple functions within, so it needs to be at like the higher level, like not at a function specific level, but in like global, if you will, or something? Like why are we defining it out here, I guess is my question.
So you could have just as, I didn't write this code from scratch, we could have just as easily for this done let root equal hierarchy here, and I don't believe this changes. Anything? No, it does not. So why? Well, so at the very least, we are going to need root in this part of the function in order to be able to call everything else that we're going to call. But why declare it earlier and then reuse it? For coding style is really what it comes down to. It's not a problem to do so. In certain languages, you are required to do that. JavaScript is not one of them. However, old habits die hard, right? So for anybody with a programming background, that may just be a more consistent way for them to actually know where everything is defined in their code.
So it doesn't have to do with like functions.
Not in this case. So, here we are creating the actual layout generator for the tree. I don't know why we call this tree map, but okay. That's confusing. That should just be tree. I'm going to fix that later. So this is the layout. We passed in a height and a width to the actual generator. So that's how it's going to know how to put those X and Y positions on everything. We are going to find our root object by using D3 hierarchy, calling it the tree data. And here, this is that optional children function accessor, right? Up here in the data, well, in this case, it does say children, so it should work if we just remove that. However, if we had something else named instead of children, this is where you would put that function in. X0 and Y0 here are kind of used to keep track of the parent positions so that we can handle animations properly later. So we're setting them here on root. And then we've got a call here where for each of the children, we're calling collapse. So collapse is going to be a function. Well, let's just finish going through and then we'll run through. We're calling collapse, and then we're calling an update function on our root variable. And our update function, like before, is going to do all of our drawing for us, right? But because we have interactivity and things are going to be created and removed, and we're putting all of that in one update call that is going to be called in multiple places. So update this is the first call here, but when we have kind of our on-click function down here, this is also calling update, right? Cool. So, what the heck is going on with collapse here? And then what does our update function look like? These are the two big open pieces in our code. Collapse. What this does is this creates, in addition to the regular children attribute, a second attribute, underscore children. And this is basically going to act as a hidden storage element for us, where when we want to hide the children, i.e. we don't want them drawn, what we're going to do is we're going to stick them in this hidden element that isn't accessed and set the actual children element to null. So it looks like there's nothing left to be drawn. And then later we're going to restore that by simply taking what's in the hidden element, putting it back in the regular one. And that's how the kind of hiding and restoring is working on the back end for here. So what we're fundamentally doing is we're changing the data with each of these calls, and the update draw call is just drawing things accordingly. And here is that click function toggle of where we're doing exactly that. If children is defined, we're going to hide them, and if it's not, then we're going to take the ones from the hidden object and stick them in the regular children attribute for that particular object. So now we've got to do our actual drawing here. We've got our tree, we've got our nodes, we know what our data is. So here, we are going to actually call the tree map command en route to generate the actual layout. So we haven't generated any of the crazy data yet until we get to this point. Here, we can get all of the nodes by calling descendants. And we can get all of the links by calling descendants and using the slice command. And then for kind of, this is normalizing to a fixed depth for each node. Then we're setting our y value to be equal to depth times 180. So this is just, we are at this point overwriting the y position that was created here to create a fixed depth. If we were to comment this out, I'm not entirely sure what it looks like. Let's see. Yeah, so at this point, it's expanding to be our full space, right? And then when the data changes and it needs to be larger, everything moves. Where what we had before by creating a fixed depth basically says, well, we know that we're going to need to expand stuff later, and so we're setting this to be consistent so that the y position of this level is always going to stay the same no matter how many things we expand or retract. Does that make sense?
So with that approach, would you ever, if you had too many elements, would it go off of the SVG?
No. With this approach, you could.
Okay.
Yes. At the same time, how that would happen is you do something like this where you naively set this to 180. Where in theory, rather than set this to 180, we have width, we know what our margins are, we know what our tree max depth is. We can calculate a number based on that to ensure that it doesn't.
Okay, so generally, if you want to go about using that fixed width approach, you would just go ahead and have to calculate that and then use that as the max y that you end up achieving.
Or be super careful with your random numbers and do a lot of manual hacking. But yeah, if I were doing this myself, what I would probably do there for something like this is I would grab the fact that we know as soon as we have root what the depth is, right? That was a value that we had, or height rather, so we pull root dot height, we take our width divided by root dot height, and at that point you've got the value you need over here. Okay, so here's the update for all of the nodes. So this is exactly what we kind of expect based on our previous data here. We've got kind of selecting object, binding data to it based on the ID. This is the enter command. This is adding that click functionality to that. Here we're appending the actual circles to that enter command. This is where we're setting the style to it. This is the appending of the text. So this is handling all of that for the entering ones. We now have the update that we're going to do to the ones that were already there, right? So we're going to merge, enter, and we're going to add transitions here to the updating ones such that they translate to their new position and change the fill colors. This is the removal of the exiting nodes. In theory, you could have done this before the merge. In this case, it doesn't really matter. We are using a transition on the exit nodes here as well. And these are simply doing changing the size and style again as part of those attributes. So basically all of this section reduces to your enter, update, merge command with the use of some transitions and updating of various attributes and styles. All code we've seen before. Maybe not in this exact realm, but for the sake of time, if you want to go through the really, really in-depth, it's posted, you can do so. Updating the links, we're going to do the exact same thing. So entering selection, an update selection, transitions, exiting, storing the old positions for the transition. So this was that X0, Y0 that we set at the very beginning. This is so you have access to it. And we are using diagonal 0, 0 here as kind of the, well, each of these links, we're creating a path. What we're setting this path to is diagonal with this object defined based on kind of your source here was part of the actual data set being passed in. Right, so when that gets changed, this is updating specifically kind of the object that's assuming X is the source X, Y is the source Y. We've created this object, we're passing it into path, and this diagonal function, and that's creating all of our paths. And so this diagonal is simply a manual path that is handling that for you for this draw. And that's what's being set here. And the end result is exactly what you see here. So for creating your, question.
So unlike Arc, we have to draw our own path manually.
I do not know the API well enough to say for certain. I believe there definitely, there is a path generator function.
Okay.
Whether or not it generates the kind of smoothly varying things that you're seeing here, I don't know.
Okay.
So that would be a question that you can address by looking at the API. But the end result is a tree here that hopefully kind of the basis, it's more complicated than the one you're going to need for homework 5, and hopefully you can use kind of code base as a way for going through and making sure that you can easily do the last part of the homework. Now, based on timing, we have 2 different options. Both of these are going to require the same intro, but we're only going to be able to have time to discuss one more of these examples in class. We've got a tree map, which is another hierarchical layout. And this is going to have the same basis as kind of pulling in from a CSV file and doing data processing in a more complex hierarchy, and you create something that looks like this. Great. And there's all sorts of complexity here because Circle will actually link you to the actual equivalent D3 code here. So there's some fancy stuff in the back end happening with how you're handling links and hyperlinks from objects and things like this. So we can go through this example if you want, or we can talk about network layouts, where we are going to talk about how you create something that looks like this. Network layouts. This is what I figured the answer was going to be, but I prepped both. We're going to give you the option. All right. So for either of these, everything that we dealt with up to this point basically had a data set that was fairly small and simple, and we declared an object and then we used it. Great. That is not going to be the majority of data sets you work with. Right? Most of them are not small enough that you're going to be like, oh, I'm going to put this JSON file in line. Right? No, instead, in this case, this is character co-occurrences in Les Mis. Right? Like, if we actually look at the JSON file, You ain't putting that in line, guys. Okay, so we can look at what that looks like. Like there's a set of nodes, which are IDs that have a group associated with them, and links that define kind of a original source node, a target node, and provide a corresponding value. But like, we're gonna have to load the file. So when we're talking about file loading, this is where we get back to, and we addressed it briefly with maps, but we're gonna do it a little more in depth. Asynchronous data loading. Right? So if we look at this particular code example here, where what we've got is we've got console log hello, we've created a load data function that's going to load a data set. When the data set's loaded, it's going to say data set's loaded, console log that. It's got a way of catching the error here, and then a console log world. So what order are we going to see these print to the console? Are we going to see hello world done plotting, or are we going to see hello done plotting world?
Probably it will be hello world.
It will be hello world done plotting every single time. This is because the D3 call is asynchronous. So basically, it's non-blocking. As soon as this is defined and this is called, this script is going to continue to execute regardless of what is happening with the other thing. And almost certainly, this is going to get hit before you ever hit anything else because you're loading a file there and that's going to take time. So, what this means in practice is that if we're doing, we'll just go back up to this one, right? If we're loading a data set like this, where are we putting all of our D3 draw calls? You need to put them here. Because if you stuck them here, you don't have access to the data, right? And in this case, that makes a lot of sense because we know that JavaScript variables are function scoped. So if you define a function, if you define a thing inside this function, you can't necessarily expect to access it outside that function. Natural extension, which just makes a lot of sense given the async and await syntax we're using here. That syntax is new as of D3 version 5. It used to be a lot more confusing. It is not anymore, so we're just not going to cover the old way of doing things because we don't need to confuse you needlessly. And also, if you try to use the old way of code, it won't work. That code will break. So if you try to use code examples looking online and you look and it's a D3 version 4, yeah, those code examples, you drop them in with D3 version 5, not going to work at all. And the fundamental changes to how D3 is handling asynchronous calls is why. So today we're going to go through the new way of doing them. So basically, what you need to understand is that all JavaScript asynchronous calls at this point are based on promises. So we're going to talk about promises, and then we're going to briefly come back to the async await syntax that we saw before. So a promise is a construct that is designed to it is designed for returning a single value asynchronously. Okay? So what happens here is that you can think about it as a placeholder. It's a container for the final result, and it's going to sit there, and eventually it's going to come back as either being fulfilled, i.e. it did what it was supposed to do, or rejected, it did not. And in the meantime, it is pending, and after it comes back fulfilled or rejected, it is considered settled. So these are the states that are involved in that promise object. What this means in your code is you are going to have various calls that return a promise object. So if you call d3.csv with the CSV file name, that actually returns a promise object. Okay? So you could async with promise right here could be d3.csv with the CSV file link that we want. So at that point, you've got two different functions here, then and catch. Then is what gets called if it comes back fulfilled. And the data associated with whatever load or whatever you do, you can just assume you could add kind of an arrow function that says data in and you got the data. That's how you're going to handle it. And this error function, similarly, you're going to have some sort of function that takes an error object if an error was thrown, if it's rejected, and you're going to do handling on it. Where this gets slightly confusing is promise then technically takes two arguments. Those two arguments are a callback for success and a callback for failure. So if you simply called same promise with then, and you passed in two functions, the first function doing the success and the second function doing the error handling, this also works. So the question is, what the heck is the difference between them? And why do we have two different ways of doing this? What's important to recognize is that promise, then, and catch, like this, assuming we just have, we're going to call F1 being our regular, how we're handling it, callback on success. And F2 is our error function, our error handler, right? So what this equates to is actually promise, then, F1 null, and then that promise goes into then null F2. So what this means from a callback standpoint and from an error handling standpoint is that if our original promise here throws the error, then this is going to, well, let's look at just promise then F1, F2 first here then. So our original promise throws the error, then we're going to get F2 called. This callback can do any number of things, some of which may throw an error. If this callback throws an error, this F2 doesn't get called. Not by definition. With catch here, it does, because in this case, if F1 throws an error, then all of the errors that are cascading from here are caught by this then, because that entire promise then is the promise for this then. And I know that that phrase coming out of my mouth was just like the most confusing thing, but hopefully my hands pointing helped make that slightly more useful, right? At a high level, what this means is .catch is going to allow you to chain things together and catch all of the errors at the end. Whereas using the promise to callback syntax, what you are going to be doing is catching various errors as you go. Which of these is more useful depends on exactly what you're doing, and there's an entire Stack Overflow discussion going through the complexities of the advantages and disadvantages and people yelling back and forth about why one is better and the other is not. You can go there, you can look, but what's important for you to recognize is that there are these two different things and ways of handling those errors, and at least now you know and can anticipate whether or not the type of error you are going to have will be caught when you make a given call. So we're just arming you and leaving it up to you to decide what the most effective way to actually call that in your own code is. But what we just introduced here is a notion of chaining. And this is super awesome for promises because the old way of handling asynchronous calls required you to nest every single asynchronous call that you wanted. And this was a design pattern that was affectionately known as callback hell. And we no longer have callback hell because instead we can do an asynchronous task and then do another asynchronous task as soon as asynchronous returns, assuming it returns correctly. and do a third one, and we can put a catch on this last one that's going to catch all of the errors from all of these all the way through. Beautiful stuff. Far nicer to deal with than trying to read if each of those functions was nested inside of one another up here, right? And so this is the benefit of promises. Async await is basically syntactic sugar introduced by ES6 for handling promises. And so the await operator, as long as it's in an asynchronous function, is going to wait on the return value of the promise. So it's going to pause that code block in the asynchronous function until the promise has returned, at which point you're guaranteed that it exists. And this allows you then, for people that are coding in other languages and know Python and things like this, you can use a standard try-catch block here now to do all of your error handling. So all the complexities of that error handling back and forth that we were doing with promises, well, you can actually go through and use await calls in asynchronous functions and do it all manually yourself in ways that you know exactly what's going on and you don't have to worry about it. Whether or not it's easier to use the async await functionality versus the promise then functionality is going to depend heavily on context. I think in the last example we're going through, I actually used the promise functionality just because. The only other thing to talk about here is in these particular versions, if we call this asynchronous function that's going to get a user, and we say let user get this, what is this object? It's a promise. Right, so you can't just go about using user at this point. It doesn't return it. User is only available inside that asynchronous function. Unless, yeah. No, we're just going to go with the unless is crazy crap you don't want to deal with. So I'm just not going to bring it up. Cool. So, in the last 10 minutes, let's go through this final example of our node link diagram. Okay, so we had our JSON file. These are Les Mis characters. I really don't know Les Mis, so like, if you're looking for your favorite character, we can do it, but I'm going to be of no help with this. So what's important to recognize here is it's talking about we're using the D3 fetch module. That's basically everything that we just talked about, back-end asynchronous loading. D3.json, in this case, is a call that is part of the fetch module that is going to do this entire asynchronous loading for us. And then the other thing here that we haven't discussed that we need to discuss for layouts are forces. When we're talking about a force-directed layout, what this does is it is something that starts in one state and various forces act on it until it hits a state of hopefully equilibrium. And the end result is going to be something that looks like that. So it's going to iterate to this by applying forces in various steps, right? So how do we handle this? Well, there is a simulation object, which is D3 forces simulation, to which we add various forces. These forces can be links, they can be many bodies forces, which basically apply to everything uniformly. They can be kind of, there's a force that specifically tries to drag things toward a centered location. We'll go through each of these. There are collision forces and there are explicit positioning forces. This simulation we're looking at right here is simulating with three forces. It's simulating with a set of links that are based on the IDs. It is simulating a charge force with many body, and it is simulating a centering force that is going to pull this stuff to the center. So in order to explain what each of those is doing, what we're going to do is we're going to look at the various GIFs here in line, and what happens as we remove one of the ones that is sitting here, right? So in this case, we removed the links. and those things kind of just distribute themselves, right? And that is exactly what the charge force is, or the kind of many body force itself is going to be doing for you. So link is going to ensure that there are links and those constraints are held. You can think about these, what's going on here as you're applying forces to each of the nodes, and that's going to stretch the connections between these various links, and then that constraint's going to get resolved like a spring, and it's going to pull things back into location. So it's going to combat whatever other forces are going on. Okay, the syntax for setting up force.link is you have to have a way of ensuring that you've set the given ID that the link objects are going to access, and then the link objects themselves need to look something like this up here, where there's a source, a target, and a value. The source is an ID from something of one of the other things. And so that is exactly what this call right here is doing, is we are saying, okay, you're going to go through the data set, and you are going to ensure that the node's ID is what we're using for our links. If it is not specified, this will simply use the index. So the reason that is in there, and as kind of a point, is very simple thing to forget, and all of a sudden your node diagram doesn't look at all like you were expecting it to. Watch out for this. Okay, the many body force, unlike the link force, is going to apply mutually to all of the different nodes. Basically, you can set it to kind of positive or negative values that are going to attract or repulse the nodes respectively. If it's not specified, it defaults to -30. So here we removed that many body force that we had in there, and all of the nodes clump together from their initial state because it's defaulting to a many body force of -30. Force.center. This is going to translate all of the nodes uniformly so that the mean position is at this centering position specified. So if we would remove this particular line, right, it's going to center everything at 0, 0, which is over here, and we are missing half of our nodes in our visualization. Right, so this is that translate thing again, and this is the equivalent call for how do you get the entire thing to move to where you anticipate it to be when you're dealing with a simulation that's going to update. The other ones that we haven't talked about, collide here is basically creating a sphere of a given size, in this case 50 radius, or it's not a sphere, it's a circle because it's 2D, around each of the nodes. And it's using that to handle collisions, right? So in this case, every single one of these you can think of has like a giant sphere around it, which is why they're all getting pushed out to the sides. If we change this to something more manageable, of course that's a GIF, so we can't do it in this example, but we can do it in a later example, then that's going to basically enforce whether or not the amount of overlap you can get between your given nodes. And then force.x/force.y are explicit positioning that set the position of given nodes and fix them so that the rest of everything simulates around it. Right? So in this case, we are setting the position of this guy and everything else is being adjusted accordingly. So, these are all the forces we're going to specify. What you do is you create the simulation, add the forces, add the nodes from the graph, and you add the links from the graph to the link force. And at this point, this is going to loosely give you everything. So SVG code here, this is color. Here's our simulation. Here's the creation of the link force where we're telling it it needs to get IDs. Here's a charge force. Here's the centering force. Here is our loading of our Les JSON. So everything here is part of the then call. That's taking the returned graph object from this JSON file, and we're creating a group. We are creating all of the lines, which is kind of the select all, data bind, enter append with the links that we saw right up here, right? These links, right? So we're going through all of those and we're creating the lines associated with them. Then we create our node groups. For each of the circles, we're going through finding the actual node data, attribute updates. We're going to add some drag listeners that we're not going to cover just because they're like click functions and they're going to allow us to drag elements around and watch what happens. And we're going to append a tooltip. So once you've got all of the things in there, you are going to call your simulation that we set up outside. We're going to put the nodes in it. We're going to line up our link force with our graph links. And we are going to define the simulation on command. This is going to actually then do the simulation. So tick is the standard kind of iteration for the simulation. And so what this is doing is it's going through, and for each tick, we are manually doing an update of the node's coordinates to move the lines and circles in place according to the underlying value. So here we're setting x1 equal to source x, y1 to source y, target 1, or x2 to target x, target y, right? These are the lines that we're drawing. We're basically taking the positions of the nodes that have been simulated and updating the line ends right now. And then similarly, we're changing the actual CX, CY position of the nodes according to that same simulated data. Error catch and the end result is your node link diagram here that you can play with. That's your basis, right? It's so at a high level, admittedly, this kind of last node link diagram, we went through the bulk code a little bit fast, but the core bases for how layouts are handled should be something that you should be able to go through the D3 documentation and figure out now. Layouts are something that go through and only create derived data for you. You handle all of the actual draw update calls yourself. And as long as you recognize that and go through and read the equivalent documentation for each of these things for how they get set up and what they expect, you should be able to use these things pretty effectively. Any major questions? All right. I think that's time. 1 minute over.